Now, sometimes you have such reactions where you do not have any solid form in it. Let's take this example. This is what we call as SHE, or standard hydrogen electrodes. So in this case, the reaction that we have is H plus becoming H2. So first, of course, balance any reactions that you see. So 2H plus 2 electrons. Yeah. And then if you take a look at the phase, this is a solution, an aqueous or an acid, in principle. H2 is a gas. So you do not have any solid form in this reaction, unlike this reaction where you have Fe solid and Ag solid. However, you need the solid electrodes because you have to connect the wiring to something that is solid, and then the solid is being soaked into the electrolytes. So whenever we do not have solid form inherently in the reactions, we use inert electrodes. Inert electrodes will help with the electrons flow. It will not be involved in any reactions. We can use platinum or we can also use carbon. Therefore, in the cell notation, normally we will see something like this. For instance, you have a reduction reaction, so this will become a reaction taking place at the cathode, of course. Cathode is always a place for reduction. So we will see this guy after the salt bridge. So this one will be the anode and then salt bridge, and then this particular half reaction. So how do we write it down? We write the aqueous phase, H plus, aqueous. We draw another line to separate H plus with H2, which is a gas. And then we draw another one to state the solid or the electrode, which in this case we can use platinum or carbon solid as the inert electrodes to help hooking up the solution to the particular wiring in an electrochemical cells, that is galvanic or voltaic cells. In a lot of cases, you will see that aqueous system will be completed with its concentration, so something molar, and the gas system will be completed with its pressure, so something atm. Now, we will talk about a standard condition in which every aqueous system has the concentration of 1 molar for aqueous, and then every gas system will have a pressure of 1 atm. This is what we call a standard condition. Of course, we can also have the non-standard ones where the concentration will become any other number but 1, and for gas it will be any other pressure but 1 atm. That will be the non-standard condition. So with that in mind, I will introduce you now to a parameter that we call as the standard potential. Again, standard means that we have all aqueous phases as 1 molar concentration and all gaseous phase in 1 atm pressure. Now, standard potential is symbolized as E0, like this. The 0 is a symbol for the standard condition as usual. And normally for standard potential, we use a reduction reaction. And this is very important for you to remember. Now, the SHE, or the standard hydrogen electrode, is the one that we use as the reference point. So the E0 for SHE is equal to 0. The unit, of course, is in volt. So E0 is equal to 0 volt for standard hydrogen electron. For the rest, you will have, depending on the values, could be positive. It could also be negative like this or positive like this one. Again, as you can see, all the reactions are written in reduction form. So the electron always is positioned at the reactant side because that is the characteristic of a reduction reaction. So receiving electrons. Now, let us compare these three different reduction reactions. So we have first the lithium ion into solid lithium. Second, we have the Zn or zinc ion into solid of zinc. And finally, we have the silver ion into solid silver. We can see here that we have three different E0 values. This one is the lowest and this one is the largest. Now, you have to remember that we are looking at reduction reaction, and normally the bigger the E0 that you have for that particular reduction reaction, that means we have an increasing tendency to undergo reduction. Therefore, say if you would like to have several different pairings, what if you pair the Ag system and the Zn system? In this case, because Ag plus becoming Ag has a larger E0 than Zn2 plus becoming Zn, Ag plus becoming Ag will undergo the reduction, and therefore it will become the cathode. Therefore, in this case, if you write down the cell notation at the cathode, you will get Ag plus Ag, and then Zn, of course, is now forced to release the electrons and become Zn to Zn2 plus. Simply because the E0 for Ag plus Ag is bigger than for Zn2 plus Zn. So, the system at the bottom, the Ag system, has a bigger tendency to undergo reduction than the second system. Undergo reduction is of course equal to being a cathode, because cathode again is a place for reduction reaction. Now, what if we now pair the Li and Zn? Between Li and Zn, we see that the E0 is bigger in value. Bigger in value in comparison to the Li. Because Zn has a higher E0 in comparison to Li, Zn will become the reduction process, and therefore it will take place at the cathode. So now, this is what we got for our notation cell. Zn2 plus will be reduced into forming Zn, and the Li will release the electron to become Li plus. So as you can see in here, depending on the pairs, one will become the cathode as long as the E0 is higher than its pair. And for this, we have what we call the potential of the cell. Sometimes we call this also the electromotive force or the EMF. Now, how do we calculate the E0 of the cell? We take the E0 of the cathode and then we subtract them by the E0 of the anode. So, for instance, for Ag and Zn system, we take the E0 of the cathode system, which is 0.80, minus 0.76. So, let's say we have first system and second system. For the first, the E cell is going to be equal to cathode, so 0.80, minus the anode, so minus 0.76. For the second system, we will have the E cell of the cathode. So what is the cathode in the second system? We have the Zn, So Zn has 0.76 now. Minus the anode, so minus 3.04. And normally in this case, you always end up with something positive, especially at standard condition, because it is a spontaneous process. Therefore, we can also connect this to the thermodynamics parameters, which is the delta G. Delta G 0 is equal to minus NFE0. E0 is the E cell that we calculate as the following. So cathode minus anode. Don't forget, everything has to be in the reduction form. F is a constant that is called the Faraday constant, and normally will be given to you in the questions, of course, as usual. While N is the number of electrons involved in the reaction. This one that I discussed in the beginning of balancing the redox reaction. So in this case, let's go back over here. N is equal to 6 because 6 electrons is being transferred or being involved in this pair of reactions. So if we take a look at these reactions, you have 2 electrons being released, you have 1 electron being accepted. So finally, first reaction, the N will be equal to 2. For the bottom reaction, the N will also be equal to 2. 2 electrons will be released by Zn, and 2 electrons will be also accepted by 2Ag+, becoming 2Ag. So again, you have to sum up these 2 reactions, and to balance it, you have to multiply the third reaction by 2. To sum up first and second reactions, you would have to multiply the first reaction by 2. And therefore, the N for both pairs will be 2, and this number is the one that you put in this reaction. And therefore, as long as the E of the cell is positive, so positive multiplied by a positive value, multiplied by a positive value, multiplied by a negative sign, then you get a negative delta G value. So if the E cell is bigger than 0, then you will get a negative value of delta G0. That means you have a spontaneous reaction.